cable that connects the projector system to the laptop was not working. Actually, about 10 minutes after I canceled lecture, I brought my own cable back in here and I plugged it right here. And it did work. So I brought my own backup just in case, although I did report that this cable was not working, so it seems like they fixed it for the time being. So there's that. As I mentioned, over Piazza and at the, I guess, right before I canceled lecture last week, everything is sort of pushed back by about half a week. So the homeworks are now due on Fridays, and the lectures are all delayed by one lecture. In terms of the core content of the course, that does not impact the course at all. There's a slack of 3 lectures built into the class. Those 3 lectures are typically a mix of either, well, they're a mix of like what people are using machine learning for in terms of contemporary research, since I think it's good to introduce students to what people use machine learning for here at Caltech, for example, on modern research questions and activities. Although, of course, since those are not core content to the course, we can sort of cut one of those lectures at no cost to the course, other than your personal sense of intellectual fulfillment, but I'm sure you'll get that elsewhere. Any questions about that? Okay, great. So let's just move right along. This is lecture 4. We'll be talking about regularization, and we'll end with some special issues pertaining to regularization in the terms of sparsity and the lasso method. But again, just to recap, and it's important just to keep hammering this home because we keep building off this pipeline, which is we start with, and again, this is for supervised learning. We start with a supervised training set where we get training pairs of XY pairs, where X is the input features and Y is the label, let's say plus or minus 1 for a classification or for binary classification, and a real value number for regression. We choose a model class or a family of model classes, so it could be more than one model class. In this case, it's just linear. And then we choose a loss function that specifies the mismatch between the ground truth label and your model's prediction. And all those ingredients get put into a learning objective, specified in the bottom left box, where we're trying to find the parameters of our model class that minimizes this loss function that we chose on this pre-collected training set. And we can solve this using, typically these days, stochastic gradient descent or a variant of stochastic gradient descent. And if we have multiple model classes, one way to choose for the best model class or to detect if we're overfitting to the training set is to do some sort of validation. In this case, I'm depicting cross-validation. And that's sort of the entire pipeline. Today, we're going to use regularization, and I'll explain what regularization is more concretely later, to think about different choices of modeling classes and how it relates to overfitting. So, what are the different choices of model classes? So, option 1 is sort of a combination of, it sort of blends together the model class and the loss function a little bit, but different learning approaches like SVMs versus artificial neural nets versus logistic regression versus least squares linear regression. Option 2, which will be the focus of today, is regularization. So how do we actually choose different regularization strengths as a form of model selection? And before I do that, let me just go into a little bit of notation about norms. So a norm is a way of measuring some quantity of, in this case, a vector. The L0 norm is not actually a norm, but I'm going to put it up here just as for conceptual reasons. The L0 norm measures the number of non-zero entries. So the formula is given on the right. The norm is specified in the bottom right subscript. Again, the L0 norm is not actually a norm under the mathematical definition of norm. I'm just putting it up here for conceptual reasons. So it measures the number of non-zero entries in a vector. The L1 norm is the sum of the absolute values of a vector W. So that's the formula right here. The L2 norm, in machine learning, we typically use the square of the L2 norm. So the squared L2 norm is the sum of squares of the entries of the vector. So the L2 norm itself is the square root of the sum of squares. And the squared L2 norm is just the sum of squares, also basically the dot product of the vector with itself. And since this is the default norm, it typically doesn't even have a subscript. So if there is no subscript, it's the default norm. Although you could also put a 2 down there. And then there's the L infinity norm, which is the max absolute value. So it's the single entry that has the largest absolute value. That's the L infinity norm. So these are some of the most common norms that people use in machine learning. There are others too. You can design L3, L4, L5, and so on and so forth. And again, L0 is not actually a norm. I just put it up here for conceptual reasons. So in this lecture, we're just going to be minimizing squared loss. So y sub I, you can think of it as a real value label, and we're doing regression. The reason, we'll just call this least squares. And we'll be focusing on squared loss for this lecture, although everything that I'll talk about, composes with other choices of loss functions as well, such as hinge loss, such as log loss. But just for simplicity, we'll just keep it as the simplest loss, which is squared loss, and talk about regularization in the context of composing it with squared loss. And for that, we get to the first form of regularized learning, other than the support vector machines that we looked at briefly in the previous lecture, and that is ridge regression. Ridge regression is the name for the following learning problem. It comes from the statistics community. And the idea is that we have, in this case, a linear model. And we're minimizing squared loss in terms of the training error, measuring training error. And the goal is to find the parameters of this linear model that minimizes this particular learning objective. Now, this particular learning objective is the sum of the original loss function that we've been thinking about for the entire course so far, plus this other term, which is lambda times W transpose W, which is the square 2 norm of W. And so this first term is what people talk about as regularization. The ridge regression, in other words, is equivalent to L2 regularized least squares linear regression in this case. And you can think of it intuitively, and we'll talk about this more formally as we go along in this lecture, as a learning objective that trades off between model complexity versus minimizing training error on the pre-collected training set. So in that case, we can think of every lambda. So lambda is a non-negative number. So it could be, if it's 0, then this just defaults to just this training loss. If it's really large, then we care more about this first term than the second term because it's the bigger term in the sum. So you can think of each choice of lambda as corresponding to a choice of model class, and we'll discuss this connection later on in the class more formally. But first, let's talk about just a very, very simple contrived toy example. So there's 2 features. The first feature is, and they're both binary, so 1 or 0. The first feature is age. Is the age greater than 10, yes or no? And the second feature is the gender male, yes or no. So binary features, so a very, very simple toy example. And then y is in this very toy example, is a binary label. Is the height greater than 55 inches or less than or equal to 55 inches? And then we have a training set. Okay? And we're going to solve this. We're going to treat this y for this, again, in this very simple example, we're going to treat this y as a real valued label. So even though it's binary, we're just going to treat it like it's real value to minimize squared loss. And so, let's say the top half is training and the bottom half is testing. What I'm showing you is what the W and B look like as lambda increases. So when lambda is 0, this is what the first row is what W and B look like. As lambda increases, you eventually, when lambda gets really, really large, actually W actually converges to 0 as lambda gets arbitrarily large. And then B converges to just a fixed offset. And then you can actually plot training and test loss as a function of lambda. So you pick a lambda, you solve this optimization problem, and you plot the training and test loss as a function of lambda. So when lambda is really low, the training loss is really, really low. As lambda increases, so as this component of the loss function becomes more important than this component, the training loss increases a lot. Now we look at the test loss in this simple example. For lambda equals close to 0, the test loss is pretty high. So this suggests that we are overfitting to the training set. as lambda increases, the test loss, even though the training loss increases, the test loss decreases. We're still overfitting, but not as much. And then as lambda increases a lot, the test loss goes back up, but the gap between test loss and training loss goes down. So even though the overall test loss is going up, it's suggesting that we're not learning as well on the generalizing as well, or excuse me, learning as well for the test distribution. The degree of overfitting is going down. It's just that the model class is now massively underfitting the training set. Okay, so here's the updated pipeline. And for this lecture, we can think of the choice, the reason why we want to use cross-validation and model selection is that we have a linear model class, we have a fixed loss function, and for the purposes of this lecture, the entire purpose of doing model selection is choosing the right lambda for this learning problem. Yes, question?
Just to confirm, so lambda is like choosing, so you're not choosing different model classes, right? It's just like choosing the model within a given model class, right?
You're actually choosing a different model class. The question is, it seems like lambda is not about choosing a different model class. And I will show you the concrete mathematical connection to choosing a model class in about 8 slides. Yes.
Last slide?
This one?
Yes. So where in your training would you actually want to stop? Like, is it when the test loss is lowest, or do you want to optimize for minimizing the overfitting, which would be?
That depends on your goal. If your goal is to have best test performance, then it's where the test loss is lowest. Yeah. If your goal is some other purpose, maybe like, well, in machine learning, that's typically the primary goal, minimizing test loss. So again, there's a bias variance trade-off, right? So you can think of the bigger the gap between test loss and training loss as equivalent to there being higher variance, and then the red line is the bias, right? So the bias variance trade-off is not optimized at this point. Yeah. So I mean, there are reasons why you may want to have may not want the lowest test loss. There are reasons maybe for interpretability, or for other reasons that are complementary to raw performance on test examples. But for this class, at least for now, we're going to ignore all those issues. Okay. So what I'm plotting here are in these 5 columns on the right is the score of the linear model that you've trained on these examples, these 2 binary feature examples. And again, this column is the target label. So the first column is just a name, the first column serves no purpose for this in this example. But these 2 columns are the 2 features. The 4th column is the label, and then the last 5 columns are the trained model on the training set, the top 6 examples, and the score that this trained model gives on each row. So in increasing lambda. So in the beginning, lambda is very low, close to 0. In the last column, lambda is very, very high, effectively infinity in the last column, at least up to 2 significant digits. So in the first column, you see that in the training set, which is the first 6 rows, excuse me, the raw score matches the label, which is this column, pretty well, and then it matches the next label, the labels in the test set slightly less well. As lambda increases, the model score predicts 0.67 for every example, and that's because 2/3 of the time in the training set the label is 1. 1/3 of the time in the training set the label is 0. And so if the bias term, if the W's go to 0 and the only thing you fit is the bias term, if the W's go to 0 as lambda increases and the only thing you fit is the bias term, then what minimizes squared loss? Well, having the bias term be the average label, which in this case is 2/3. So as lambda becomes infinity, I mean, you can also verify for yourself, for example, as lambda becomes infinity for this optimization problem, then any w that is non-zero gives you infinite loss. Gives you an infinite cost on this learning objective. And we're trying to minimize this learning objective. So if lambda is infinity, or as lambda becomes arbitrarily large, there's an incentive to learn a w that is exactly 0, or close to 0, in which case all the learning happens in b, which is just a single parameter, which if w is actually exactly 0, b is just the average label, because it's just y minus b squared. It's just y sub I minus b squared over all the training examples. And that's why you get this behavior. And then the one that has the best test error is somewhere in the middle. The leftmost column, in terms of the model score, overfits the training set too much. And the test error is higher than in the middle column, which in this particular toy example somehow balances the bias variance trade-off. And of course, it probably comes as no surprise to many of you that the best choice of lambda depends on the training size. So here is a plot of test loss as a function of lambda of another synthetic example, in this case 25 dimensions, for 25 training points, for 50 training points, for 75, and for 100. So in particular, the best lambda for 25 training points is somewhere over here, and the best choice of lambda for as you get to 100 is actually the lowest lambda. The lowest lambda actually has the best test loss for 100 training examples, although it's pretty close to this one. But okay, just to recap, we talked about ridge regression, which is just another name for L2 regularized least squares. This is what it looks like mathematically. Larger lambda corresponds to more stable predictions. If lambda is infinity, I'm just going to predict, in my simple example, 2/3 for all training examples. I'm going to ignore the features. I'm just going to predict 2/3 all the time. If we think about stability of a prediction, that's an incredibly stable prediction. It's not very accurate, but it's stable. Less likely to overfit to the training data, but of course, if your lambda is too large, you will underfit to the and therefore you won't predict well in the test set either. Question, yes?
Sorry, in the last slide, is there any particular reason why it's so these curves are so not smooth? I guess intuitively I expect.
Oh, so the question is, why are these curves not smooth? And the answer is I only tried like 5 or 6 choices of lambda. I could also try like 100 different choices of lambda. I guess I was lazy. Yeah. Yes. Okay. You're right. I could have tried like 100 or 1,000 different choices of lambda, and I didn't do so.
And so the reason there's always that kink is because there's one point there and then one point at the end, and then one point at the end.
Yeah. That's right. Yeah. I guess I tried 4 choices of lambda. Yeah. I could have tried 1,000, in which case it would look smoother. Okay, maybe I should rerun this experiment for the purposes of making this slide clear. But the reason why there's the kink is because I only tried 4 choices of lambda, which in practice is probably what you should do. Like, okay, maybe, okay. And this is probably more reflective of what you do in practice. In practice, you're not going to try like 1,000 different choices of lambda. You would try like powers of 10 or powers of 2, or some sort of multiplicative scaling, which would look like this. Like, it's typically in practice not worth micro-optimizing lambda. Question, yes?
Is it a general trend that as the number of training points goes up, the lambda would work better if it's smaller?
Yes, as a general trend, yes. So it's a general. So maybe if you hold on to this question for about like 5 more slides, it'll make more sense. Yeah. The final thing I'll say on this slide is that this regularization, you can compose it with other choice of loss function. You can replace squared loss here with hinge loss, log loss, whatever. You could do L2 regularized a hinge loss, which is exactly the support vector machine, by the way. You could do L2 regularized log loss, which is just regularized logistic regression. It's exactly composable in exactly the same way. Nothing changes except the derivations of the gradients get more complicated. Okay. Also, an aside on stochastic gradient descent. This term here, you can think of it as, again, this loss function is additively decomposable. And there's many ways to additively decompose it. So remember when we talked about stochastic gradient descent, we talked about how you can interpret, if the loss function is additively decomposable, you could interpret a stochastic gradient as this random variable that in expectation is equal to the gradient of the full loss function. And there are different ways to additively decompose if you have this regularization. Here's just one way, where I just add, if there's n training examples, I just add 1 over n of the regularization to each of the subcomponents for my stochastic gradient descent. That's one way to do it. There's other ways you can do it as well. Okay. Now we're going to talk about the question that was raised earlier in the beginning of this lecture, which is what is the connection to a model class? It seems like this lambda doesn't directly correspond to a model class, at least not the way we discussed in class so far. It just seems like a tuning parameter of an optimization problem. So is there a connection? There is. And let's talk about norm-constrained model classes. So imagine that I had a class of linear models, although it doesn't have to be linear, but let's say it's linear for now. But instead of having W be anything, we're going to say it's a class of linear models where let's say the L2 norm, the squared 2 norm of W, is less than or equal to some constant C, where C is a parameter of my choice. So in the 2D case, for C equals 1, the class of linear models where the square 2 norm of W is less than C equals 1 is everything in here. I guess this is I guess there's a slight error on this. This should be maybe this would be C squared, but anyways, I might be off by a square here. But anyways, the picture is still fine. So this is C equals 1, everything in here, and everything in the green circle is for C equals 2, and everything in the blue circle is C equals 3. Right. This is a model class. It's the class of all linear models whose square 2 norm, L2 norm, is less than some constant C, less than or equal to some constant C. Okay. Now, there seems to correspond to this learning objective. So as you increase lambda, and you look at the L2 norm of the solution of the W, so you solve this optimization problem, you get a W, you compute the L2 norm of this W, and you plot it against lambda, which is this bottom right plot. There seems to be a connection, right? As you increase lambda, the L2 norm of the W that we're learning gets smaller and smaller and smaller. So there seems to be a connection. Can anyone tell me how you can formally establish this connection if you've taken multivariable calculus? Don't be shy. Yes?
It's the Lagrangian.
Correct, Lagrangian. Or let's start with Lagrange multipliers, then I'll get to the Lagrangian. Let's talk about Lagrange multipliers. Okay. So in this very simple example, we're just going to have one training example, so just one XY pair. And we're going to completely ignore the bias term, the B term, for simplicity. And then what you see in this plot is the loss function of this optimization problem, of this one example. And then the yellow line is the negative of the gradient. So we're trying to do gradient descent. So the yellow line is the negative of the gradient. So if you're at this point, sorry, if you're at this point, you want to go in this direction because it's the negative of the gradient. If you're at this point, you want to go in this direction because it's the negative of the gradient. and then that's, and the direction, the size of the arrow is the magnitude of the gradient. Okay, now we're going to constrain. So now I'm going to say we're only interested in linear models, W, whose L2 norm or squared L2 norm is less than or equal to C. So all the W's, in this space. Okay, so if we're here, then no, that's the gradient. So we can do gradient descent. If we're here, the gradient actually takes us outside of the class of models that we're interested in. Because if we follow gradient descent from this point, then we'll end up in a model that lies outside a model class, because its L2 norm will be greater than C. So what people do is, one thing you can do is you can say, well, I'm just going to project. I'll do what's called projected gradient descent, and I'll just project back onto the boundary of my model class, because I don't want to leave it, because that's my specified model class. And then we'll get to this point in this example, and that's the gradient, right? And then, well, actually, this particular point is exactly normal to the boundary of the model class. So if I project it, it'll project right on back onto the original point. In other words, because it's exactly aligned with the normal of the boundary of that point, the gradient loss function and the tangent and the normal of the boundary are exactly aligned. What that means is that there exists a lambda. There exists a lambda greater than or equal to 0, such that the gradient of the loss, right here, is equal. There's a negative sign here to make the signs aligned. To negative lambda times the gradient, the normal of the boundary of the surface, which is exactly specified by this formula. Okay, so this looks like a standard model class that this looks like it's something that fits into the standard definition or notion of model class that we've been talking about for most of this class. Right, we're defining a class of models. In this case, it's the class of linear models where the 2 norm of the W is constrained to be less than or equal to C. And since I'm a machine learning person, I'm not going to distinguish between 2 norm and squared 2 norm. So I'm going to abuse that notation during this entire class. So please excuse that if you're someone who's more mathematically precise in that regard. By looking at the example from the previous slide, we had this observation that one of the optimal solutions of this problem, at the optimality of this problem, where the gradients, the gradient updates takes you back to the original point, which is called which is a place where the gradient is 0 effectively. There must exist a lambda where this property holds, where the gradient of the loss function is exactly aligned with the normal of the constraint boundary. These two conditions must be satisfied at optimality. And that can be derived from what's called the Lagrangian. Now, there are many different forms of the Lagrangian. They all vary by a little bit. There's a generic form. I decided to use this particular form because it was more mathematically convenient for this class. And so the Lagrangian is basically saying, well, I'm going to treat lambda as a parameter in my optimization problem. So the claim is that solving the Lagrangian also solves the original norm constraint optimization problem. I'm going to go through this a little bit fast. Of course, there's many things written about the Lagrangian on Wikipedia and many places. But I'm just going to go over this a little bit fast, just to give you a flavor of why this is connected to model classes. So what is an implication of the optimality condition of Lagrangian? Well, at optimality, the gradients must vanish. That's one of the definitions of optimality. So we'll take the gradient of this Lagrangian with respect to W and set it equal to 0. If you take the gradient with respect to W, set it equal to 0, you get this condition, right? So the gradient of the loss equals is aligned in direction with the normal of the constraint boundary. You just take the gradient of this guy. Sorry, there should be a T transpose. And you take a gradient of this guy, and you get this. So that satisfies the first condition. We could also take the gradient of lambda, right? The gradient of lambda over here. Well, if W transpose W is less than C, then this guy gets zeroed out, so we get 0. If W transpose W is greater than or equal to Z, greater than or equal to C, well, this term is just linear in lambda, so the gradient is just this guy. It was greater than or equal to C, which means that if we set the gradient here equal to 0, it must be the case that W transpose W is less than or equal to C. And this satisfies the second condition, that W transpose W is less than or equal to C. So if we're actually able to solve the Lagrangian at optimality where the gradients are equal to 0 for both W and lambda, the solution that must satisfy these optimality conditions, which means that it's an optimal solution for this constrained optimization problem up ahead at the top. And this is a fairly standard derivation. This is a fairly standard application of the Lagrangian in this particular form of a constrained optimization problem that you see at the top. The Lagrangian is used for all manner of constrained optimization problems. We just applied it to this particular case where we're thinking about norm-constrained model classes. Whoops. Okay, so now now I'm going to sort of close in on this connection. So we have a norm-constrained model class. We have L2 regularized learning, which is what the example we went over in the first part of this lecture. The claim is that they're equivalent, and that you can establish the equivalence through the Lagrangian. In particular, for any choice of C, there exists a lambda such that solving this optimization problem solves the, sorry, let me rephrase. For any choice of C, so referring to the top left learning objective, which is your standard model class type of definition, there exists a lambda such that the solution of this guy is the same as the solution of this guy. Okay? But for a fixed lambda, this guy just looks like this guy, assuming that the learning objective, assuming that the solution is exactly C. So for a fixed lambda, this will give you, for every C, we can choose a lambda such that the solution of this guy looks like this guy, which means the 2 norm of W is exactly C, which means this guy has the same solution as this guy, and which will give you a 2 norm which is exactly C. In other words, for every choice of C in the top left, I can choose a lambda such that the top right gives me the exact same W. And that's what we saw in this plot right here. For every choice of C, so this plot, is sort of transposed to what I just said. I said for every choice of C, there exists a lambda that gives you that 2 norm. Here, it's like for every choice of lambda, it gives you a certain C. But you can see that there's a close relationship. And in the non-degenerate region of this relationship is a bijection. So it doesn't matter which direction you say the implication. Any questions on that? Okay, so just to recap, we spent the first maybe 20 minutes of this lecture talking about L2 regularized regression, also known as ridge regression. Then we spent some time talking about a more standard notion of a model class, which is we're going to use linear models, but we're going to constrain the parameters to live inside some L2 ball of L2 norm at most C. Through the Lagrangian, we establish that these two learning objectives have, at least in the non-degenerate choice, for non-degenerate choices of lambda and C, there's a bijection between the two, such that for every choice of C, which is the more conventional form of a model class, for every choice of C, there exists a lambda that gives us the exact same solution to the two problems. Large lambda leads to more stable predictions because the W that we get is a smaller W. It's less likely to overfit to the training data. And if the lambda is too large, we'll underfit, and so we also won't do well in the test set. And indeed, we can see that for different choices of lambda, this indeed is a measure of the model complexity, right? So for C, if C is 1, then if we choose two different model classes, so C equals 1 and C equals 2, all the models in C equals 1 are contained in the models for C equals 2. So the model class for C equals 2 is a strict superset of the model class of models in C equals 1. So it's by definition more complex. Just like all linear models are contained in quadratic models, where the quadratic coefficient of the polynomial is set to 0, we think of model complexity here as terms of supersets and subsets. Or at least that's one way to think of a model complexity, where you can actually directly compare the complexity of model classes. So, and because of this relationship, now we can say that, okay, if we want C to be smaller, we want lambda to be bigger to get the same solution. Therefore, as you increase lambda, you are decreasing the complexity of the model class you want to learn. And again, everything I just said works with other loss functions as well, such as hinge loss, log loss, etc. The only reason I'm just sticking with squared loss is just that it's just mathematically more convenient to write on the a slide. Yes?
Is the loss function necessarily convex in lambda?
For a proper norm and for a convex loss function, yes. So if the question is this learning objective necessarily convex in lambda? If your norm is convex and this loss function is convex, then the answer is yes. So the L0 norm is not actually a norm. All proper norms are convex. Yeah. Well, I shouldn't say that. All proper norms that we use in machine learning are convex. I shouldn't. I should be a little bit careful. You guys are Caltech students. All proper norms that we use in machine learning are convex. Yeah. Beyond that, I haven't really done the full, thorough thought. There are optimization problems that go beyond machine learning, so I don't want to say too much. Okay, I'm going to talk about a minor point that I think is very interesting. And that's on the equivalence between regularization and hallucinating data points. Again, we're going to omit the bias term for simplicity, so just look at the W. So assume B equals 0.
Previous question, he asked if it is convex in lambda, or what was the question?
Is this learning objective convex in lambda? So if this term is convex, I'm sorry?
Isn't it always linear in lambda? Isn't it just it's a linear?
Oh, I see the question. So maybe the question was, is the whole thing always convex? I interpreted, okay, I see, okay. Since this is linear in lambda, it's always convex in lambda. No. So if you look at the Lagrangian, I could create a constraint boundary that is not, so the constraint boundary has to be convex, right? So this max thing, so like if the constraint boundary is not convex, then this is not, even though it's linear in lambda, the coefficient behaves in a can make it behave in a non-convex way. So for the Lagrangian to be convex, the boundary of the constraint set has to be a convex shape, which is true for a norm and is not true in general. Okay. Okay, so I'm going to spend like a minute talking about a cool result in hallucinating data points and its relationship to regularization. Okay, so this is our standard L2 regularized ridge regression learning problem. And so this is the gradient of this learning objective with respect to W. So the gradient of this guy with respect to W. So I'm going to, instead of doing this explicit regularization, let's instead hallucinate some data points. In particular, let's hallucinate D data points of the following form, where capital D is the dimensionality of the input feature space. And the D data points we're going to hallucinate look like this. So it's going to be square root of lambda times the dth basis vector. So the dth basis vector is just the vector that is 0 everywhere except for 1 along the dth dimension. And then the label is going to be 0. Okay, so this is our synthetic training point that we're going to create. We're going to add that to our training set. So rather than regularizing, we're just going to hallucinate these capital D training examples and just add that to our training set and just train in an unregularized way. And that looks like this. So we have a normal training loss over the normal training set, and then we have this training loss over a hallucinated training set. Let's take the gradient of this guy. Wow, it looks exactly like the gradient of the L2 regularized learning objective. And you could verify for yourself later. It's a pretty standard derivation. Identical. What does that mean? That means that from a behavioral standpoint of the learning objective, this regularization is the same as simply saying, I'm just going to pretend in the absence of any training data that I have these capital D training data points with a label 0. It has the same effect on the learning objective, at least for squared loss. And this relationship between regularization and hallucinating data points actually comes up time and again in different types of learning problems. There's actually often a formal relationship between the two. So if you want to regularize your training data or your learning problem and you're not sure exactly how best to regularize it, one thing you can do is just augment your training data set with synthetic examples of what you think should be default behavior in the absence of training data. And just add that in, and they just learn as usual. And sometimes there's a formal, explicit formal connection. Other times it's just an intuitive thing, and it just kind of works. These days, this is also known as data augmentation. If you read about trying to figure out how to regularize deep neural nets so that it's more robust to adversarial examples and all that other stuff. Data augmentation is a commonly practiced technique that people use. This is a very simple form of data augmentation that in this particular case has a very formal, explicit connection to regularization. In general, of course, it's hard to establish that's a formal connection, but at an intuitive level, that connection is always there. Okay, the other small thing I want to talk about before I talk about sparsity and lasso is multitask learning. So suppose I had two prediction tasks. Like I want to train two spam filtering methods, one for Alice and one for Bob. And let's suppose that Alice and Bob are similar people, so they have similar preferences about what is spam and what is not spam. And so furthermore, let's assume that the training sets for Alice and Bob are both relatively small. So we have these two training tasks, and their training sets are relatively small. So option one is, well, let's just train the two models separately. Again, we'll just use squared loss for simplicity. And just treat as two separate supervised learning problems and just call it a day. But both models have high error because the training sets are really small. Option 2 is to train jointly. So we're going to learn the parameters of W and V for the two tasks. I'll just call the second task the parameters V. Okay, this doesn't actually do anything because I can just additively completely decompose these two learning objectives because these two learning objectives don't interact with each other. So the fact that I added them together changes nothing. So here's one way to do multitask regularization. So in the absence of training data, I prefer W and V to be close to each other. And what does that mean? That means that W and V should be, this is basically the 2 norm of the distance between W and V, right here. So in the absence of any training data, I prefer W and V to be close to each other, and I penalize that distance with this regularization term right here. And now you see that this is test loss as a function of gamma for a fixed lambda. So as gamma increases, that means I prefer the W and V to be close to each other more. The test loss decreases. And then as gamma gets too big, which means I effectively want W and V to be the exact same vector. If gamma is infinitely big, then I pay infinite penalty if W and V are not exactly the same vector. As gamma gets really big, then I actually suffer higher test loss because the two tasks are not exactly the same. So this is an instance of multitask regularization. So you can construct different regularization schemes to fit the needs of your learning task as your learning task starts to get more and more complicated. Although this type of stuff is largely outside the scope of this class. Okay. Any questions? Okay. So for the remaining 25 minutes or so, I'm going to talk about lasso, which is L1 regularized least squares regression. So we looked at ridge regression, which is L2 regularized, and now we're going to look at L1 regularized. So L1 regularized ridge regression is is what you see in the top left. Their standard L2 regularized is in the top right. And the biggest difference is the regularizer. Actually, the only difference is the regularizer. In L1 regularized least squares regression, the regularizer is the L1 norm, which is the sum of the absolute values of the components of W. Whereas in standard ridge regression, we use L2 norm, which means the regularizer is the sum of squares of the entries of W. So one way to think about the differences between L1 and L2, well, first is to plot the regularizer. So the L2 regularizer looks like the blue line, and the L1 regularizer looks like the red line on a per entry of W basis. We can also think about when these two regularizers have equal gaps. So for L2, in terms of the increase in the cost, again, the absolute numbers, the absolute scale is irrelevant because I could just shift them up and down by a multiplicative factor, and it doesn't matter. What matters more is the shape of the loss function. So for L2, going from 0 to 1 incurs the same regularization penalty as going from 1 to root 2. For L1, going from 0 to 1 gives you the same regularization penalty as going from 1 to 2. So it's linear. Whereas in L2 or squared L2 regularization, as we always use in machine learning, it's quadratic. Okay, so I want to briefly talk about subgradients, which was mentioned, which was asked about last week. How do you actually take the gradient of a function that's not differentiable? The hinge loss, which is what we talked about when we talked about SVMs, is not differentiable. There's a corner in the loss function. Even though the function is continuous, it's not discontinuous, it's continuous. There's a corner which is not differentiable, which means the gradient doesn't exist. But as long as these functions are convex, which this is, it's a convex function, the subgradient exists. And the subgradient is simply the set of the set of slopes in the 1D case, it's the set of slopes that sit under the function. So if the function is differentiable, the subgradient is exactly the gradient. Or in other words, the subgradient is a singleton set. In the case where the function is not differentiable, then the subgradient is actually an actual set with more than just a singleton item in it. So in the case of the L1 regularization penalty, if the component of WD is less than 0, so it's on this slope, then this is a differentiable function. It's a linear function. It's differentiable, and the subgradient is exactly the gradient, which is just -1. If it's on the positive part, again, this is a differentiable function. Over here, it's linear. It's differentiable, in which case the subgradient is exactly the gradient. It's +1. At exactly w equals 0 is where the function is not differentiable. The gradient doesn't exist. The subgradient is the entire interval from -1 to +1. Because all the slopes, all the slopes from -1 to +1 sit underneath this function at 0. So the subgradient is a set of all possible slopes from -1 to +1. There's an entire theory about convex analysis that deals with subgradients. It's beyond the scope of this class. The important thing is just that this is what a subgradient is for the purposes of this class, and this is how we take the subgradient of the L1 norm if you want to do gradient descent. And indeed, you can do subgradient descent rather than gradient descent, or stochastic subgradient descent. It completely generalizes. You will not be asked to do that in this class, but this is how it works underneath the hood. Yes?
So you just like randomly choose a value from the subgradient?
So the question is, do you just randomly choose a value from the subgradient? And the answer is no. There are more sophisticated methods. If you're interested, I believe there's a link to on my website called Iterative Soft Thresholding, and which will actually talk about how to do that properly. Okay, let's go back to Lagrange multipliers. So now we're going to look at model classes whose L1 norm is less than or equal to C rather than L2 norm. So what does that look like? Well, okay, the first examples are the same. That's L2 norm right here. This is L2 norm. The purple line is L1 norm. So geometrically, if you constrain the L1 norm to be less than or equal to C, then I'm interested in all, in this case, 2D linear models that live inside this purple diamond. And so if I were to do gradient descent, or subgradient descent, here's, if I'm at the boundary here and the gradient point or the negative of the gradient points in this direction, then I take a step in there, and eventually I'll get to this point. Let's say if I keep doing gradient descent along the boundary, I'll eventually get to this point. And now there are, again, the subgradient, so the normal to this corner, so the gradient of the L2 norm is equivalent, mathematically equivalent to the normal of the circles that's the boundary of the L2 constrained model class. For L1 constrained, the boundary is this diamond which has corners, and in this corner, the way we think about it is that the normal vector to that corner is a continuous set of vectors. All those vectors are valid normal vectors to that corner, and as long as there exists, as long as one of those normal vectors matches the gradient of the loss in terms of direction alignment, then you'll get stuck there in a gradient descent. It'll it'll be an invariant point, which means it'll be a solution to the optimization problem. In other words, there exists, in other words, the gradient of the loss function is contained in some scaled, is contained in the subgradient set, appropriately scaled by lambda. In the case where the boundary is differentiable with no corners, then the condition was that these two are equivalent, and this is just a singleton gradient. In the case where it's not differentiable, you have this corner, then we talk about subgradients, which is a set, and this is the optimality condition. Yes, question?
So why does it make sense only for the points where the function is not differentiable?
It makes sense everywhere. It's just that it's a singleton set when it's differentiable. So this definition makes sense everywhere. It's just that in the cases where the function is differentiable, this set is a singleton. So then it's just an equivalence rather than contained in.
Yes, but why can't we pick a point where, why can't we change this definition to having multiple norms even at other points?
I'm not sure I understand the question.
This definition sounds a bit artificial. I mean, why do we only have multiple norms in the points where
multiple tangents, multiple subgradients?
Yes. Yes.
Okay, I'm not qualified to answer this question. If you're interested, we have this class called ACM113, optimization and convex optimization, which will answer that question probably more than you want to ever know. It has to deal with what's called duality. It's well beyond my ability to properly explain, although I took the class in grad school. It's well beyond my ability to properly explain, but that is the definition that people use. Some people here took ACM 113, right? One person, at least one person is nodding. Okay. If you're really interested, I'm happy to work it out with you during office hours. I don't want to take the time to go over it in class because it's well beyond the scope of this class. Okay. Sorry, question. Yes.
Do you think with sufficiently precise numbers or discrete what you do, do these subgradient still come up?
Yes. If I understand your question correctly, I think it's related to my next point, which is that the solution to the L1 regularized learning objective tends to be at the corners of the boundary. Right? Sorry, go ahead.
But couldn't you preclude like that exact point such that we just get this arbitrary?
Right. Oh, okay. So the question is, if we use stochastic gradient descent or stochastic subgradient descent, won't we overshoot the corners? We won't exactly hit the corners. And that is a limitation of stochastic gradient descent, not a limitation of the characterization of the solution of this optimization problem. And so there's a method called iterative self-thresholding, or ISTA, which actually exactly hits the corners. It's a slight modification of gradient descent. So a qualitative observation is that many of these solutions to this type of learning problem will have solutions where many of the dimensions are at the corner. So this is just, so many of the solutions will be at corners, which means that many of the W's will be 0. That's where the corners are. Many dimensions will have 0 in the entries. So now let's talk about sparsity. Vector W is sparse qualitatively if it's mostly 0. Most of the entries are 0. In other words, a vector W is sparse if it has very small L0 norm. Now, why don't we do L0 suppose we cared about sparsity, why don't we do L0 regularization? Well, it's for the same reasons why we don't do 0-1 loss. It's because it's not continuous and it's flat everywhere. It's flat or discontinuous everywhere. So instead we use a surrogate for L0 loss, which is L1 loss. L1 loss, as we explained qualitatively in the previous slide, tends to have solutions at the corners of the boundaries of the model class. And those corners are exactly places where at least one of the parameters of W is 0. And it's continuous, and that's why we use it. So L1 regularized regression, in this case, is the preferred learning objective of choice if you want to learn a W that is sparse, that has many 0 entries, and relatively few non-zero entries. Why is sparsity important? There are many, many reasons why people want sparsity, depending on the problem that you're trying to study. One is simply for computational or memory efficiency, right? So, if I know that my solution is sparse and my vector is, let's say, I don't know, 1,000,000 in this particular example, and I know that, let's say, there's only 2 entries that are non-zero, I can either store 1,000,000 numbers, most of which are 0, or I can store 2 numbers like a linked list or a lookup table, where in this case it's just the index value pair. And anything else not explicitly stored is assumed to be 0. One of these is way more efficient than the other. The dot products are also more efficient. And sometimes the true W is sparse. There's an entire field called compressed sensing, from which a lot of this machinery and terminology is borrowed from, where they assume that the actual W that we care about actually is sparse. And so we want to actually recover not only a good predictive model, but exactly which entries of W is non-zero, also known as the support of W. So here's a flavor of relatively classical these days, but still kind of interesting guarantee. So suppose that we have data generated according to this distribution. So the Y is just a Gaussian corrupted observation of some W transpose X, or W star, excuse me, where W star is sparse. So this is an assumption of how the data is generated. And W star is truly sparse. And we care not just about predictive accuracy, but which entries of W, when we estimate W from W star, is actually non-zero. We care about that for reasons of interpretability or some other reason. Then for a specific choice of lambda, that depends on the dimensionality and the size of the training set. With high probability, and the probability increases with the size of the training data, the support of W, the W that we learn, which is also just the entries of W that are non-zero, is a true subset of the support of W star. What that means is that we will only have true positives and not false positives. Like if this entry of W is non-zero, I have reason to believe that it truly is non-zero in W star that generated the data. And then in this other condition, which is related to the size of the training data, if the training data is sufficiently large, then I can exactly recover the support of W star. And there are many applications that want to do this, often for reasons of interpretability. So this is just a flavor of a learning theory analysis. Again, I'm not going through the proof. If you're interested in the proof, you can click on one of the links in the bottom. But this is an informal statement of actually a learning theory analysis guarantee. Yes, question?
By assuming that it's sparse W, aren't you just basically saying that I've made a bad choice in the features that I'm measuring to try and construct this label Y sub I for each X sub I? Because for those entries of W that are 0, those features in X then don't matter anymore at all. They're not predictive of your label at all.
So the question is, did I make a bad choice in collecting X if W star is sparse? And the answer is that it's complicated. So I know that W star is sparse, but I don't know which ones. So you can't rule anything out a priori. Yeah. Okay, so this is the same toy example that we had before, and now we're looking at the effects of L1 versus L2 regularization. I'm just going to zoom in on the part down here. One of the, I should mention, this is actually a plot. This is actually a plot of the two dimensions corresponding to the first feature and the second feature as a function as lambda changes. So as lambda changes, the W looks like the red line for L2 regularization, or sorry, for L1 regularization, and the W looks like the blue line for L2 regularization. And this is, it's a little bit hard to see. I guess it was, it'll be a little bit more clear in a different example. But you can see here that there comes a point where this red line is exactly 0. Whereas for L2 regularization, as you increase lambda, the W gets closer and closer to 0, but is not exactly 0. But for L1, it exactly goes to 0 because it goes to the corner of the boundary of the model class. Okay, let's see. Aside optimizing lasso, I think this was actually asked like several times. How do we actually optimize for the lasso objective? If you do gradient descent, it's hard to hit it. One of the reasons why people want lasso is they want to exactly zero out a bunch of W's. But with gradient descent, with the step size and all that, it's hard. If your goal is to exactly zero out a W, it's hard to actually exactly zero it out with gradient descent. And so there's an extension to gradient descent called iterative self-thresholding. It's an extension of gradient descent. And the intuition, although again, if you're really interested, you should read a formal description of ISTA. The intuition is that if the gradient causes the W of that dimension of W to pass 0, then we're going to clamp it at 0. So what that means is, if we're right here, and the gradient causes us to pass 0, we're going to clamp it at 0. That's what self-thresholding does. But again, it's beyond the scope of this class, but if you're interested, there's a link that sort of describes it in pretty nice detail. For those of you who want to use L1 regularization in like PyTorch or TensorFlow, one of the big deep learning packages, it'll just do it automatically. It's like soft thresholding. Any questions? Okay, so just to recap, lasso, which is a name that has been associated with L1 regularized least squares regression for a long time. It comes from the statistics community. Lasso learns a sparse weight vector. One of the things that's interesting about L1 regularization is that the model you learn, the W that you learn, is often not very accurate. So it has very high loss in the training error, even though it can help you recover the non-zero entries. So what people often do is they run lasso, L1 regularized least squares regression. They look at the non-zero entries selected by lasso, and then they rerun an unregularized least squares regression on just those entries, so with no regularization, or with a very small amount of L2 regularization. Because lasso is often not good at actually. Lasso is good if your model is actually sparse. Lasso is good at figuring out which entries of your model should be 0 versus non-zero. In practice, it is less good at learning the weights, the actual weights of the non-zero entries. So that's why people do this two-step approach. It's very common. So for example, this is very common in biology, computational biology, where if you want to learn the interactions of a gene regulatory network, and you know that the interactions are sparse, you run lasso, and you figure out which interactions are non-zero, and then you rerun least squares regression unregularized on just those features selected by lasso. It's a very common thing that people do in practice. Another thing is that if you believe that the true model should be sparse, or you just want a sparse W for whatever reason, it's easier to inspect. It's more interpretable, right? If you have a million-dimensional feature vector, and you only want to recover the top 10 or top 100 entries, then and you want to manually inspect your model, it's impossible to manually inspect a million, but you can inspect up to 100. And there's this, well, okay. Maybe this last part is a little bit more complicated than just ease of optimization. Mathematically, lasso is much trickier to optimize because of this corner that gradient descent will not hit exactly if left to its own devices. But with things like soft thresholding, lasso can be trained very efficiently. So it's trickier, but it can be trained much faster because then you can snap. You know that you can snap a solution exactly to zero in certain cases, which is more efficient than gradient descent by itself. So it's a little bit of a complicated issue, but beyond the scope of this class. Just to recap on regularization, we have L2 regularized least squares regression, also known as ridge regression. We have L1 regularized least squares regression, also known as lasso. We have multitask. And as your learning task becomes more and more complicated, and you start to think about what makes sense in terms of constraining your model, what you want your model to learn or not learn, you could design your own regularizations. Multitask is one that I kind of sort of made up for the purposes of this lecture, although other people use it as well. But I just thought, I have two small data sets, I know the tasks are related. How do I encourage the two vectors to be close to each other without overruling the training data? I came up with this regularization. So you can come up with your own as you look at more and more complicated learning problems. So this is the pipeline. And the model selection here for controlling model complexity is simply choosing lambda, which is equivalent to choosing, in this case, a linear model class where the W's are constrained to live in a bigger or smaller norm ball. Okay, so for the next lectures, we'll go through decision trees, bagging, random forest, ensemble methods, and this slide is for last week. Sorry.